Hello again guys and welcome to the second part of lecture 5B. In this video, we will look into some of the quantitative applications of acid-base titrations. These are the learning outcomes for this learning video. At the end of these topics, you should be able to enumerate and discuss the reactions taking place in each step of the Kjeldahl process, explain the use and limitations of the Kjeldahl process, execute calculations using molarity and normality in a Kjeldahl-related problems, and lastly, discuss and apply the concepts of double indicator method in determining the constituents of a carbonate mixtures. An application of the acid-base titration is the elemental analysis involving the determination of nitrogen. Developed in 1883, the Kjeldahl and nitrogen analysis remains one of the most accurate and widely used methods for the determination of nitrogen in substances such as protein, milk, cereal, and flour. Now, the main objective or purpose of this procedure is the oxidation of organic compounds using concentrated sulfuric acid. However, not all types of nitrogens can be quantified in the Kjeldahl method. Certain aromatic heterocyclic compounds such as pyridine and its derivatives are particularly resistant to the complete decomposition by sulfuric acid. Aside from this, nitrogens belonging to the azo, azoxy, and nitro groups are also converted to the nitrogen gas or to its oxide, and the results will give you negative determinant errors. For many years, the protein content of foods has been determined on the basis of total nitrogen content, and the Kjeldahl method has always been universally applied to the determination of nitrogen content. Now, the nitrogen content is multiplied by a factor to arrive at the protein content. This approach is based on two assumptions. First is that the dietary carbohydrates and fats do not contain nitrogen, and secondly, that nearly all the nitrogen in the diet is present as amino acids in proteins. Now, on the basis of early determinations, the following values are used to convert the percent nitrogen content into the protein content as shown in this slide. Now, let us look at the processes involved in the Kjeldahl method. In this method, a certain substance or sample is heated in the presence of sulfuric acid. This acid breaks down the organic substance via oxidation, and the reduced nitrogen in the form of ammonium sulfate is liberated. The potassium sulfate is usually added to increase the boiling point of the medium, and catalysts such as mercury, selenium, copper, and ions of mercury or copper are also used in the digestion process. Now, the sample is fully decomposed when we obtain a clear and colorless solution. In the next step, the distillation of the solution now takes place, and a small quantity of sodium hydroxide is added to convert the ammonium salt into ammonia. The distilled vapors are then trapped in a special trapping solution of HCl or hydrochloric acid and water. In the next step, the amount of ammonia or the amount of nitrogen present in the sample is then determined by back titration. As the ammonia dissolves in the acid trapped in the solution, some of the HCl is neutralized. Now, the acid that is left behind can be back titrated with a standard solution of a base such as sodium hydroxide or any other bases. In some cases, ammonia is collected in boric acid solution, and the reaction is shown here. Now, the excess borate is then back titrated with a strong acid as shown in this equation. Let us now look at this short animation video to see the nitrogen determination in coal by the Kjeldahl method. Alright, so after watching the video, now let's just look at a typical example for Keldal analysis. A 0.200 gram sample containing urea with a formula mass of 60.05 and a structure of urea shown below is analyzed by the Keldal method. The ammonia is collected in a 50 ml of a 0.05 molar sulfuric acid, and the excess acid is back titrated with 0.050 molar sodium hydroxide, a procedure requiring 3.40 ml. Calculate the percent urea in the sample. So you're given here the reactions involved in the problem. Alright, so you should realize that this is a simple back titration problem. The first thing we can do here is to determine the total moles of the acid by multiplying the concentration of the acid to its volume. The total moles of the base can also be calculated by multiplying the concentration of the base to its volume. Then the amount of the acid that reacted is calculated by subtracting the total moles of the acid, which is 2.50 times 10 raised to negative 3 mole, to 1.70 times 10 raised to negative 4. Take note to use a stoichiometric factor in this case. That is, 2 moles of sodium hydroxide is required to react with 1 mole of the sulfuric acid. Now, the net amount of sulfuric acid is calculated to be 2.42 times 10 raised to negative 3 mole. We can readily compute or calculate the percent urea in the sample by a factory label approach as shown in this slide. Overall, the percent urea in the sample is 72.60%. Okay, so let's try to look at another problem. A 0.7121 gram sample of wheat flour was analyzed by the Keldal method. The ammonia formed by addition of the concentrated base after digestion with sulfuric acid was distilled into 25.0 ml of a 0.04977 molar HCl. The excess hydrochloric acid was then back titrated with 3.97 ml of 0.04012 molar sodium hydroxide. Calculate the percent protein in the flour. Just like what we did earlier, the first thing that we need to do here is to determine the total moles of the acid by multiplying the concentration of the acid to its volume. In a similar manner, the total amount of the base can be calculated by multiplying the concentration of the base to its volume. Now, the amount of the acid that reacted can be determined by subtracting the total moles of the acid, which is 1.244 times 10 raised to negative 3 mole HCl, to 1.593 times 10 raised to negative 4 mole sodium hydroxide. The net amount of hydrochloric acid is then calculated as 1.085 times 10 raised to negative 3 mole. Again, we can readily compute or calculate the percent nitrogen in a sample by a simple factor label approach as shown in this slide. The percent nitrogen in the sample is 2.13%. We can now determine the percent protein in the sample by multiplying the percent nitrogen which we computed with a factor that is 5.70%. Finally, the percent protein in the sample is 12.14%. So this will be your first self-assessment question for this lecture video, and you can pause this video to answer this question. Another application of acid-base titration is the use of double indicators to determine the relative percentages of carbonate mixtures or the determination of alkalinity of a substance. Now, the main source of natural alkalinity are carbonates, bicarbonates, and hydroxide compounds. The analysis of such mixture requires two indicators, one with the alkaline range indicator and the other with an acid range indicator. Now, the composition of the solution can be deduced from the relative amounts of the acid titrant that is needed to titrate equal volumes of the sample. Now, I will explain how this is done in the succeeding slides. Alright, so in a solution containing sodium carbonate, sodium hydrogen carbonate, and sodium hydroxide, no more than two of these three constituents can exist in appreciable amount in any solution. For example, in carbonate mixtures, sodium hydroxides and sodium bicarbonates are incompatible mixtures. Since sodium hydroxide is a strong base, this can react with sodium bicarbonate to yield sodium carbonate. So this means that we will never have a mixture of sodium hydroxide and sodium bicarbonate because they will react together. So if a solution contains excess sodium hydroxide, then the mixture will contain sodium hydroxide, and sodium carbonate. While if you have an excess of sodium bicarbonate, then the mixture will contain sodium bicarbonate and sodium carbonate. Before looking at the mixtures of carbonates, let us first familiarize ourselves with the titration of sodium carbonate, or commonly known as soda ash. Okay, so soda ash is a primary standard for HCl, or hydrochloric acid, and soda ash is a weak dibasic compound. So this means that we have two equivalence points. Now the first equivalence point occurs at pH 9, or 8.3 to be exact. Now this corresponds to the half neutralization of the carbonate to bicarbonate. In our titration curve, the phenolphthalein changes from pink to colorless. So at this point, we have already consumed AML of the titrant acid. Okay, so the second equivalence point occurs at pH 4. This corresponds to the neutralization of the bicarbonate to carbonic acid, which dissociates into water and carbon dioxide. At this point, the methyl orange changes color to red. Now, the second endpoint is always used for the standardization because the change in pH is greater than at the first endpoint. Since the stoichiometry of both reactions are 1:1, then we expect that we will use the same volume of the acid that was used to reach the phenolphthalein endpoint to change the color of the methyl orange. Okay, so in double indicator method, the composition of the solution can be obtained using the volumes of the acid used in reaching each endpoint. Once the composition of the solution has been established, the volume data can be used to determine the concentration of each component in the sample. Now, the following figures shown in this slide are the titration curves and indicator transition ranges for the analysis of mixtures containing hydroxide, carbonate, and bicarbonate using a strong acid titrant such as hydrochloric acid. Alright, so I will discuss in detail these figures during our synchronous discussion. This table shows the summary of the volume relationships in the analysis of carbonate mixtures. In this table, the first column presents the chemical species that are present in the medium. Now, the second column is a double indicator carried out in a single vessel. So this means that after reaching the phenolphthalein endpoint, the second indicator is added into the same flask. The corresponding volume relationships of the acid titrant required to reach the phenolphthalein endpoint is denoted by V1, while the volume of the acid required to reach the methyl orange endpoint is denoted by V2. In the third column, this is a double indicator method carried out in two different vessels. In this case, the first vessel is added with phenolphthalein and another aliquot is added with bromocresol green, or another second indicator. Now, the first aliquot containing phenolphthalein indicator is titrated with the acid until the endpoint is reached. Then, the second aliquot containing the other indicator is then titrated with the same acid titrant. I will now discuss what happens if we titrate a mixture of sodium carbonate and sodium hydroxide with a standard HCl titrant. Before we add hydrochloric acid titrant, the addition of the phenolphthalein indicator to a solution containing these compounds will give a pink-colored solution. Then, we titrate the solution with HCl. Sodium hydroxide is a strong base while sodium carbonate is a weak base. So it is safe to assume that sodium hydroxide reacts with HCl first completely and only then does sodium carbonate reacts. The complete neutralization of sodium hydroxide ions will require a certain volume of the acid, let's say AML. Once the sodium hydroxide has completely reacted, it's now the turn of sodium carbonate to react. Now the sodium carbonate reacts with HCl in two steps. The first is that the carbonate is half neutralized to bicarbonate. So when sodium carbonate is converted to sodium bicarbonate completely, the solution is weakly basic due to the presence of the bicarbonate. At this instant, the phenolphthalein changes its color since it requires this weakly basic solution to change its color. So we see here a change from pink to colorless. Therefore, remember that phenolphthalein only changes color when weakly basic sodium bicarbonate is present. At this point, additional volume of the acid has been used, so let's say BML of the acid titrant. Okay, so we now add methyl orange after the phenolphthalein endpoint is reached. So this will impart a yellow-orange color to our solution. As we keep adding hydrochloric acid titrant, the pH again falls, and when all the bicarbonate completely reacts now to form sodium chloride, carbon dioxide, and H2O, the solution becomes weakly acidic due to the presence of the weak acid carbonic acid, which dissociates to carbon dioxide and water. At this instance, the methyl orange changes color since it only requires the weakly acidic solution to do so. Therefore, remember, methyl orange changes color only when carbonic acid is present. At this point, we have consumed another volume of the acid, which is BML of the acid. Now let us try to analyze the volumes of the titrant acid that is used up for the first and second reaction. It is clear that the volume of the acid required to change the phenolphthalein is A plus BML, while only BML is required to change the color to the methyl orange. Therefore, if the volume of the acid required to change the phenolphthalein color is greater than the volume of the acid required to change the methyl orange, then we have a mixture of sodium hydroxide and sodium carbonate. We can also readily determine the total volume of the acid required to fully neutralize the sodium hydroxide. This is just the volume of the acid titrant required to reach the phenolphthalein endpoint minus the volume of the acid used to reach the methyl orange endpoint. We can also see from this figure that the total volume of the acid that is required to fully neutralize the sodium carbonate is equal to twice the volume of the acid titrant from the point where phenolphthalein had changed color up to the point when methyl orange changes color. Let's now look at what will happen if we titrate a mixture of sodium carbonate and sodium bicarbonate with HCl. Before we add HCl titrant, the addition of the phenolphthalein indicator will again give a pink-colored solution because of the basic sodium carbonate. Then, we titrate this solution with HCl titrant. Sodium carbonate is a stronger base with respect to sodium bicarbonate, so it is safe to assume that sodium carbonate reacts with HCl first completely. The half neutralization of carbonate to bicarbonate ions will require a certain volume of the acid, let's say AML. When sodium carbonate is converted to sodium bicarbonate, the solution is weakly basic due to the presence of the bicarbonate ions. Again, the phenolphthalein changes color since it requires this weakly basic solution to change its color. At this point, remember that the solution contains two sources of bicarbonate ions. The first source came from the half neutralization of carbonate, and the second source is from the bicarbonate from the sample. Obviously, this bicarbonate species will require different volumes of the titrant, as we shall see in the succeeding slide. As we keep adding the titrant acid, which is HCl, the pH again falls, and when all the sodium bicarbonate reacts with the acid, the solution becomes weakly acidic due to the presence of the weak acid, carbonic acid, which can dissociate to carbon dioxide and water. At this instance, the methyl orange changes color from orange to red since it requires this weakly acidic solution to do so. Now let's look at the volume of the acid titrant that was used to titrate the bicarbonate species. The neutralization of the bicarbonate, which is coming from the carbonate, will require AML of the acid, while the bicarbonate coming from the sample will require another volume of the acid, so let's say BML. Now let us try to analyze the volumes of the titrant acid that was used up for the first and second reaction. It is clear that the volume of the acid required to change the phenolphthalein color is AML, while A plus BML is required to change the color of the methyl orange. Therefore, if the volume of the acid required to change the phenolphthalein color is less than the volume of the acid required to change the methyl orange color, then we have a mixture containing sodium bicarbonate and sodium carbonate. We can also see here that the total volume of the acid that is required to fully neutralize the sodium carbonate is twice the volume of the acid required to reach the phenolphthalein endpoint. Finally, we can also say that the total volume of the acid titrant that is required to fully neutralize your bicarbonate that is coming from the sample is equal to the volume of HCl from the point where phenolphthalein had changed color up to the point when methyl orange changes color. That is A plus BML minus the volume used to reach the phenolphthalein endpoint, which is A ml. Okay, so let's try to answer this problem and apply what we have learned. A 1.200 gram sample of sodium bicarbonate, sodium carbonate, and sodium hydroxide, either alone or in permissible combination, is titrated with cold 0.5 molar HCl. With phenolphthalein as indicator, the solution turns colorless after the addition of 30.0 ml of the titrant. Methyl orange is then added and 5 ml more of the acid is required before this indicator changes color. Determine the composition and calculate the percentage of the components in the solution. Okay, so before going to our calculations, we have to realize that this problem involves a single vessel titration, since methyl orange was also added on the same reaction vessel after the phenolphthalein endpoint was reached. The next thing to do here is to analyze the volumes of the titrant acid that were used to reach the endpoint in order to deduce the components in the mixture. In this case, we use 30 ml for V1, which is the volume of the titrant acid required to reach the phenolphthalein endpoint, while an additional 5 ml or V2 of the acid was used to reach the methyl orange endpoint. In this example, we see that the volume of the acid required to reach the phenolphthalein endpoint is greater than the volume of the acid required to reach the methyl orange endpoint. Therefore, we say that our mixture contains sodium hydroxide and sodium carbonate. Okay, so once we know the components in the mixture, we now have to determine the volume of the titrant acid required to fully neutralize the sodium hydroxide and sodium carbonate. Applying what we've learned, we can say that the volume of the acid to fully neutralize sodium hydroxide is 25.0 ml, while the volume of the acid required to fully neutralize sodium carbonate is 10.0 ml. After calculating these volumes, we can now use simple stoichiometry to relate the volume of the acid, or HCl, to the mass of sodium hydroxide in the sample as shown in the numerator of this equation. Now, dividing this by the weight of the sample and multiplying it with 100 gives us a percent weight of sodium hydroxide in the sample to be 41.7%. In a similar manner, we can use simple stoichiometry to relate the volume of HCl to the mass of sodium carbonate in a sample, as shown again in the numerator of this equation. Take note that the reaction will require 2 millimoles of HCl per 1 millimole of sodium carbonate. Now, dividing this by the weight of the sample and multiplying with 100 will give us the percent weight of sodium carbonate in the sample, which is 22.1%. Alright, so let's try to have another problem. A solution of sodium bicarbonate, sodium carbonate, and sodium hydroxide, either alone or in permissible combination, is titrated against standard HCl. A titration of a 50 ml portion to the phenolphthalein endpoint requires 22.1 ml of a 0.1 molar HCl. A second 50 ml alico requires 48.4 ml of HCl when titrated to the bromocresol green endpoint. Determine the composition and calculate the molar solute concentration of the original solution. Okay, just like what we did earlier, the first thing we have to do here is to determine whether the titration was carried out in a single vessel or separate vessel. Based from this problem, a second aliquot of the analyte solution was added with bromocresol green. Therefore, this means that a double indicator was carried out in separate vessels. Okay, so just like what we did earlier, we have to analyze the volumes of the titrant acid that were used to reach the endpoints in order to deduce the components in the mixture. In this case, we used 22.10 ml of the volume of the titrant acid that required to reach the phenolphthalein endpoint. In a separate vessel, it required 48.4 ml of the acid to reach the bromocresol green endpoint. In this example, we see that the volume of the acid required to reach the phenolphthalein endpoint is less than half the volume of the acid required to reach the methyl orange endpoint. Therefore, we say that our mixture contains sodium bicarbonate and sodium carbonate. You can pause this video and refer back to our slide number 20. Once we know the components in the mixture, we now have to determine the volume of the titrant acid required to fully neutralize sodium carbonate and sodium bicarbonate. So we can say that the volume of the acid to fully neutralize sodium carbonate is twice the volume of the acid required to reach the phenolphthalein endpoint. So that is 2 times 22.1, and this is equal to 44.20 ml. Take note that the titration was carried out in two separate vessels. The 48.40 ml is the volume at the beginning of the titration down to the bromocresol green endpoint. So this means that this volume of the acid also included the reaction of sodium carbonate and bicarbonate in the sample. Therefore, in order to get the volume of the acid titrant that was used to neutralize the bicarbonate component only, we have to subtract 48.40 ml to 44.20 ml, and this will give us 4.20 ml. We can now use stoichiometry to relate the volume of HCl to the moles of sodium carbonate as shown in the numerator of this equation. Take note that the reaction will require 2 millimoles of HCl per 1 millimole of sodium carbonate. Dividing this by the volume of the sample will give us the molar concentration of sodium carbonate to be 0.0442 molar. In an analogous manner, we can also use stoichiometry to relate the volume of HCl to the moles of sodium bicarbonate in the sample as shown in the numerator of this equation. Now, dividing this by the volume of the sample will give us the molar concentration of sodium bicarbonate, which is 8.4 times 10 raised to negative 3 molar. Okay, so this will be your second self-assessment question for the quantitative determinations of mixtures. Before you start answering this problem, you have to first figure out whether the titration was done in a single vessel or a double vessel titration. Then after that one, based from the volumes that are required to reach the endpoints, we have to determine which species are present for each mixture, or if there's only one species for each problem. Okay, so I presented here the answers for the self-assessment question to check if you got the correct answers. This table shows the different applications of acid-base titrations with respect to elemental analysis. So you have here the elemental analysis of nitrogen, sulfur, carbon, halogens such as chlorine and bromine, fluorine, and phosphorus. Okay, so let's try to look at this problem. Limestone consists mainly of the mineral calcite, which is calcium carbonate, with a formula weight of 100.09. The carbonate content of 0.5413 gram sample was measured by suspending the powder in water, adding 10 ml of 1.396 molar hydrochloric acid, and heating to dissolve the solid to expel the carbon dioxide. So you have here the reaction involved. The excess acid required 39.96 ml of 0.1004 molar sodium hydroxide for the complete titration of a phenolphthalein endpoint. Find the percent weight of the calcite in the sample. Alright, so before we go to the actual computation, you have to realize that this problem is again a type of a back titration problem. Okay, so we can actually compute for the millimoles of hydrochloric acid by multiplying the volume to its concentration, and this will give us 13.6 millimoles of HCl. In a similar manner, we can compute or determine the millimoles of sodium hydroxide by multiplying the volume and its concentration, and this will give us 4.012 millimoles of sodium hydroxide. Again, just like in any other back titration problems, we can get or determine the millimoles of HCl that reacted by subtracting 13.6 millimoles of HCl with 4.012 millimoles of sodium hydroxide. Now take note that this reaction is a 1:1 ratio. Now calculating the millimoles of HCl that reacted is equal to 9.588 millimoles of HCl. We can relate the millimoles of HCl to the mass of calcium carbonate using a simple stoichiometric relationship and a factor label approach as shown here. Now dividing this with 541 milligrams of the sample and multiplying it to 100, we'll get a 88.64% of calcite. Okay, so this will be your third self-assessment question, and you can again pause this video and try to answer this question. So this is the last slide for this lecture video, and I will see you during our synchronous discussion.